eddy currents and eddy current losses. In this lesson, the learner will be able to explain the eddy current and its losses, derive the expression for eddy current losses. Have you ever played the free fall ride in an amusement park? It is a very exciting ride. Once the people occupy the seats in the ride, the gondola will rise to the top of the tower and then free fall till the ground. But just before reaching the ground, it slows down and stops. What makes it to decelerate and finally stop? It's the eddy current induced in the tower. Let's understand the phenomenon of eddy current breaking in rider. Free fall consists of a tower made of a cylindric conducting material standing on copper cylinder with the same diameter. The gondola is made from an aluminum cylinder. It has same diameter as the tower with vertically cut flat sides where permanent magnets are mounted. The magnetic fields due to the permanent magnets travel down as the gondola drops fast from the top of the tower. Once the gondola reaches the copper part of the tower, it starts to slow down because, as per Faraday's law of electromagnetic induction, an EMF is induced in the tower due to the change in the magnetic field linking the tower. As the tower forms a closed structure, the induced currents due to this EMF flow in circular paths resembling the swirling eddies formed in the rivers. Hence these currents are called eddy currents. The magnetic field due to eddy current decelerates the gondola and stops it at the end of copper part of the tower. Similarly, eddy currents are present in rotating electrical machines. As the rotor rotates in the magnetic field, it cuts the magnetic flux and EMF will be induced in the armature conductors. In the same way, as armature core also cuts the flux, an EMF is induced in the core. This EMF causes circulating currents to flow in the rotor core. Induced EMF depends on the flux enclosed by the path. That is, pi max is equal to B max into area of the loop, where pi max is equal to maximum flux enclosed by the path. B max is equal to maximum flux density. As the eddy current flows in the whole surface of the rotor core, the resistance offered by the rotor is minimum due to maximum cross-sectional area, and hence the induced eddy currents will be maximum. These eddy currents create resistive losses in the rotor which are transformed into heat. The power loss due to this is called eddy current loss. It is obvious that if the cross-sectional area of the eddy path is reduced, eddy current losses will also be less. For analysis purpose, let us consider a rectangular core instead of cylindrical core without loss of any generality. This can be achieved by using several thin electrically insulated plates called laminations stacked together to form the core instead a solid block of iron. These laminations are insulated from each other so that the eddy currents cannot circulate across the laminations. Shorter the distance between the laminations, greater is the suppression of eddy currents. From physical consideration, we have seen that thin plates each of thickness tau are to be used to reduce eddy loss. Let us derive an expression for eddy loss in the following section for a thin plate and try to identify the factors on which it will depend. Consider a small elemental rectangular closed path ABCDA of thickness dx and at a distance x from the origin. Let height of the core be h and length be L. Area of the loop ABCD is equal to 2hx. Flux crossing the loop is equal to Bmax 2hx sin omega t. The loop may be considered to be a single coil through which time-varying flux crosses, so there will be induced voltage in it. The RMS voltage induced in the loop E is equal to root 2 pi f Bmax 2hx. Resistance of the path through which eddy current flows, R path is equal to rho into 2h plus 4x whole divided by L dx, where rho is equal to resistivity of the material. Power loss in the loop dP is given by E square by R path. By substituting R path, power loss is reduced to E square L dx by rho 2h. Then the total eddy current loss after substituting values of E square and integrating the variable x from the limit x is equal to 0 to tau by 2. The power loss equation can be formed as volume of the thin plate is equal to HL tau. Eddy current losses per unit volume is given by. Finally, the eddy current losses equation is reduced to P eddy, that is equal to Ke into F square into Bmax square into tau square. So the factor which affects eddy current losses are eddy current constant Ke, frequency F, maximum flux density Bmax, and thickness of the plate tau, and is also inversely proportional to the resistivity of the material. Summary. This brings us to the end of the lesson. In this lesson, we have learnt about eddy current and its losses. Expression for eddy current losses.